So since we're working with the radius, I find it and a circle. I find it easier to think of the elemental area in terms of polar coordinates. And so our elemental area in polar coordinates equals r, which is going to be our distance from the center, times dr d theta. And when we substitute in our elemental area and simplify this, we're going to combine these. It's going to be r squared times another r, we're going to have r cubed. And I substituted in k, which stands for constant, for our max stress over our max radius. For any given rod, this is going to be, for any given rod under any given torque, this is going to be a constant. So it's just easier to do the math for me if I can use as few variables as possible. So I just call this a constant. So we have a constant times our distance from the center cubed dr d theta, and when we integrate it, we're going to have our moment. And when you do a double integral like this, you want to take the inside integral first. And so we're going to come up with kr to the fourth over 4, and that's going to be, and now we're going to do the outside integral. So we have kr to the fourth over 4 from 0 to 2 pi. And so at the time, this was a solid rod. So we went from just 0, which is the minimum possible distance from the center, to whatever point we're looking at. So to r, whatever that distance is from the center. And when you integrate that, it just comes out to kr to the fourth over 4. And now we're going to integrate in terms of the angle. And we're thinking about the entire cross section. So that's going to be from angle theta equals 0 all the way around to theta equals 2 pi. And when we integrate this, we come out with our moment equals kr to the fourth over 4 from 0 to 2 pi. And I'm sorry, there's going to be kr to the fourth theta from 0 to 2 pi. And when we substitute in 2 pi for theta, we get our moment equals our constant times our radius to the fourth over 4 times 2 pi. Simplify, and we get k times pi over 2 times r to the fourth. And if you'll recall, this is the equation that you work with to solve for stress and strain due to torsion. And when you're solving these problems, you're going to get different things given, anything from the angle of twist to the strain to the stress to torque, and you have to use any of the equations that we went through to develop this main equation in solving those problems. So you can't just memorize this and be able to solve all the problems. You really have to understand how it's formulated, and that's why I went through and did that. if you want to find out, if you want to see how the formula for a hollow rod is, how the formula for the hollow rod is developed, all you do is you go back to this step right here, where instead of from 0 to whatever distance from the center we're looking at R1 to R2. And so R1 is going to be our inner radius, our inner distance from the center, and then R2 is going to be our outer distance to the center. And this is all going to be the same, but our integration is going to be a little bit different, because instead of the 0, we have kr2 to the 4th over 4 minus kr1 to the 4th over 4, and so that's d theta. And we're going to do the same thing from 0 to 2 pi for theta. So we have kr to the 4th over 4 minus kr1 to the 4th over 4 theta. And then that's from 0 to 2 pi. Substitute in, and you substitute in and factor out, and you're going to get k pi over 2 times r2 to the 4th minus r1 to the 4th. So this is going to be for your hollow rod and your solid rod. For different shapes, if it's like a square beam or something like that, you're going to have to develop that in a different way, because the deformation is not occurring in the same plane. Like in any rod, every point in the plane is going to move, and it's going to move in that plane relative to every other point in that plane. But once you get a square rod, some of that, there's some other sorts of twisting going on. So just remember, what I've developed only works for a solid rod or a hollow rod with a circular cross section.